All right. Good morning, class. How are you? Can you hear me? Can you hear my voice?
Yes, sir.
Oops. All right. Let's do it again. Can you hear me?
Yes, sir.
Okay. Yeah, sure.
Yes, sir. Good morning, sir.
Good morning. So let's get started with the lecture. And I assume you can see my screen as well, right? Can you see my screen? Yes? No? Can you see the screen?
Yes, sir.
All right. Yeah. Okay. So in the last lecture, we had an introduction to the Unit 5, which is dams and their characteristics. And today we are going to continue the same unit. We're going to start with the design of the dams today, and probably we will continue this for the next lecture as well. Now, we are going to focus on gravity dams. If you remember, gravity dams are usually made of concrete, and they resist the forces acting on them, mainly because of the self-weight of the dam. So that is why they're called gravity dams. And today we are going to see what are the different forces acting on these dams and how we can calculate these forces. So here you can see a list of forces that we need to consider when you want to design a dam, starting with hydrostatic pressure, which is because of the water. I'm going to show you a sketch of these forces as well, but before I show you that, I want you to see the list of forces. So one is the water pressure because of water in the reservoir, and also you have water on the downstream of the dam. And then you have weight of the dam, which is going to resist all the forces that are trying to destabilize the dam. And you have uplift pressure because of water seeping underneath the dam. And you have pressure or earthquake loads when you have an earthquake event happening, and silt pressure when you have sediment being accreted in the reservoir. And you would also have wave pressure. These waves are generated because of wind, and we would have wind pressure itself, and finally ice pressure. So we are going to look at each of these forces in detail today, and we are going to design a dam. So this is how all the forces on the dam are going to act like. So you have the main dam structure itself, which is in black, and you have the reservoir water level on the upstream, which is indicated by the blue line, and you have the tail water level on the downstream, which is indicated by this blue line. Now, to look at the forces acting on this dam, because of this water level, you would have hydrostatic pressure, which is varying linearly from the surface to the bottom. So at the surface, the pressure is zero, and as you go down, the pressure is going to increase with depth. Similarly, on the downstream side, you would have the pressure because of the water, hydrostatic pressure. So it is zero at the surface, and then it is going to increase linearly. Now, this hydrostatic pressure is going to act from left to right, and it is going to act at the centroid of this triangle from the base. It's same on this side as well. It is going to act on the dam, and it is going to act at the centroid of this triangle from the base. Now, the second thing you need to consider is the vertical pressure because of this water. Now, if your dam has a triangular shape on the upstream, then you would also need to consider the vertical force or the vertical pressure because of the water on top of the dam. Similarly, here on this sloped face on the upstream, you need to consider the vertical pressure because of the water. Now, if you have sediment up to this level in the reservoir, then you would have pressure due to that silt or sediment as well. You need to consider that pressure and calculate the force resulting from that pressure. Now, because you have soil foundation here, below the foundation it's all soil, the water is going to seep through the soil, and it is going to exert uplift pressure on the dam. So it is going to act upwards on the base of the dam. So your self weight is acting downwards and your uplift pressure is acting upwards. So this is going to destabilize the dam. So the magnitude of this uplift pressure is usually on the upstream side, it is going to be gamma h, where h is the total depth of water in the reservoir. On the downstream side, it is going to vary as gamma h bar, where h bar is the depth on the tailwater. And in between, it is going to usually vary linearly. So between gamma h to gamma h bar, it is going to vary linearly. But in this case, you have drainage. So a drainage is usually provided to allow the water is seeping through the foundation and through the pores of the dam to be released. So if you are releasing the water or allowing the water to drain through this drainage gallery, then your uplift pressure is going to decrease, and the decreased magnitude of this uplift pressure is usually taken as this, where you have gamma h is the uplift pressure on the downstream side, plus some additional pressure because of the difference in the head between upstream and downstream. So now, instead of varying linearly, you have the pressure drop from gamma h to this value, and then from here, you would have a linear drop to gamma h bar. So this is because of the gallery that you're providing in the dam. So I can show you an example of how a gallery looks like.
Excuse me, sir.
Yeah.
So kindly explain about the dynamic pressure.
Yeah, I will show you that. So before the dynamic pressure, I'm going to show you the gallery. So this is what the gallery is going to look like inside the dam. So it is going to be present along the length of the dam. And there are multiple purposes for this. So one is to drain the water that is seeping through the dam. And the other is if you want to provide electrical wires or cables inside the dam. For example, if you are generating hydropower, then you can use this space to provide some cables. And also, if you want to do some maintenance of the dam, you can use these galleries. Now, we will go back to look at the dynamic pressure as well. So the dynamic pressure is a resultant of earthquake forces. Now, if you have earthquake happening, then you would see the acceleration of the water either horizontally or vertically. Now, because of this acceleration of the water body, you would have dynamic pressure. And this dynamic pressure is going to be zero at the top and then increase non-linearly. So this is non-linear increase in the pressure, and whereas the hydrostatic pressure is a linear increase in the pressure. So this is the dynamic component because of the acceleration of the water bodies. Now you can also have dynamic pressure when you consider waves. For example, you have wind blowing on top of the reservoir. If the wind is blowing on top of the reservoir, it is going to start generating waves on the reservoir. So these are called wind generated waves. Because wind is going to exert shear force or shear on the water surface. So because of this shear by the wind, the locally generated wind waves are going to be generated, and these waves are going to propagate towards the face of the dam. Now, because of this winds, you would have dynamic pressure as well. So the dynamic pressure is a resultant of either earthquakes or wind waves. So these are the forces acting on the dam that you need to consider. Now, not all the times you would consider all the forces acting on the dams. So for the design of dams, there is an IS standard code, IS6512. Now in this design standards, so they give a combination of different forces that you need to consider depending on the situation. For example, you have load combination A, which is when you have the dam constructed, but there is no water in the upstream or the downstream of the dam. And load combination B is when you have normal operating conditions, like where you have full reservoir level on the upstream and some tailwater on the downstream. And it's not during a flood, or it is not a condition where you are expecting extreme flows. So this is normal operating conditions. And load combination C is when you would have a flood discharge coming into the reservoir. So the water level is going to be at the maximum flood elevation, and then you also have uplift. And then there is combination D, which is a combination of normal conditions A, when the dam has been just constructed, and you have an additional earthquake force. And you have combination E, which is combination of B plus earthquake, but you do not consider any ice pressure. And then you have combination F, when your galleries or the drainage that you provided in the dam is inoperative. So then you would have higher uplift pressures. And then you also have the final combination G, which is E plus extreme uplift. So you have different combinations of forces that you can consider depending on the situation. Now we are going to look at in detail about each of these forces by designing a dam. So we will actually start with the design problem and see how each of these forces can be calculated. So yeah, just as I said, if there are no drains or gallery provided for drainage, then the uplift pressure is going to vary linearly. So this is a design problem that we are going to solve today. So the problem statement is like this. So you have to design a gravity dam at a reservoir site where the bed level of the foundation is at 110 meters above mean sea level, and the design reservoir full level or the full surface level of the reservoir is at 200 meters above mean sea level. And the tailwater condition is 115 meters, And you also have a wind that is blowing on top of the reservoir at a speed of 150 kilometers an hour over a fetch of 20 kilometers. And you also have the average depth given along the reservoir. So you are required to calculate the design force, the forces acting on this dam, and check for the stability. Now, the stability of this dam is going to be based on how the dam is resisting the forces, mainly the horizontal forces, and then if the dam is stable against overturning. So you would have all the destabilizing forces acting on the dam in the horizontal, and the dam has to be safe against sliding. And then the dam has to be safe against overturning. So when you consider moments of all the forces acting on the dam, the negative moments should be stabilized by the positive moments. So if you have clockwise moments, they should be counteracted by anti-clockwise moments for the dam to be stable. Now, as I said, the gravity dams are usually made of concrete. So we are assuming for this design purpose, we are using concrete, which with a specific gravity of 2.4. And then we are going to start designing the dam. So here I have a sketch of the dam, and I also have annotations for different dimensions for the dam. So starting with the top width of the dam, I have chosen as B, and the bottom width of the dam I have chosen as capital B. Similarly, the depth in the reservoir is represented by capital H on the upstream, and it would be H bar on the downstream. And you have a silt level at 120 meters. And I have shown the data that is given in the question, that the bed is at an elevation of 110 meters, and the full reservoir level is at an elevation of 200 meters, and the tailwater is at an elevation of 115 meters. Now, once you have this depth H in the reservoir, for the dam, you need to provide a freeboard so that the water is not overflowing or the water is not going on top of the dam itself. So to prevent the overflowing or overtopping of the dam, you need to provide a freeboard above the full reservoir level, which I represent by FB. And then you also have a vertical portion on the upstream of height C to provide, if you have, for example, any sluice gate that you can provide in this region, in this portion of the dam. And then you have a sloping upstream face where you can provide a spillway for the discharge to be let into the downstream tailwater. So now I want to start with the top, or the top width of the dam, which is small b. So small b, usually you select it based on the requirements for the dam. For example, on top of the dam, if you want to have a single lane road where you can have vehicles moving on the dam for maintenance, or if you want to have connectivity between one end of the dam to the other end of the dam through a single lane road, then your top width is going to be fixed based on the width of the road that you are going to provide on top of the dam. So if you do not provide any lane or road on top of the dam, then the width can be reduced. So in this case, I'm assuming that I want to provide a single lane road on top of the dam with a width of 3.75 meters. So I'm assuming the width of the road itself is 3.75, and then I'm offsetting on both sides for shoulder. So you have a total top width of 5 meters. So this is based on my assumption that I want to provide a road on top of the dam. Now, if you want to provide 2-lane road, then it could be increased. Now, the bottom width of the dam is usually calculated based on an empirical formula, which is ratio of the total depth of the reservoir divided by the specific gravity of the material that you are using. So this comes from the IS standard. So H divided by square root SC. So where H is the depth of water on the upstream. So if I go back to this sketch, my H would be 200, which is the full reservoir level, minus 110. So that's going to be 90 meters. Now, based on this, you can calculate what B is going to be. So that comes to be around 58.1 meters. So this is the B that I got from this formula, which is 58.1 meter. So I can assume the width B to be 60 meters. So this would be my starting assumption that the width is 60 meters. And based on this dimension of the bottom width, we are going to calculate the forces and see if this is sufficient to withstand the forces. Now, so then we have small h. So we know what is the big capital H, which is simply 90 meters. But to get what is the total height of the dam, we need to calculate the freeboard. So the total height of the dam is dependent on the freeboard that you want to provide. Now we are going to see how you can calculate this freeboard. So the total height of the dam is dependent on the full reservoir level, which is H. And it is also going to be dependent on locally generated wind wave heights. So as I showed you, or as I just mentioned to you earlier, the wind that is blowing on top of the surface on the reservoir is going to exert shear on the water surface, and it is going to generate some wind waves. So these are locally generated wind waves. So if you want to provide freeboard, you need to consider what is the height of this water wave height above the still water level or above the full reservoir level. So you need to calculate what is the wave height because of the wind. And then the third is you can provide the freeboard based on the wind height. And then you also have wind setup. So I want to explain the concept of wind setup here again. So let's say so that is my dam, and this is the water level. And you have wind generated waves that are approaching the dam. Now, because of the wind generated waves, you have momentum that is being put into the water column. And because of that momentum, you see this is the initial full reservoir level. Now, this is going to slightly increase towards the face of the dam. So now it is not horizontal anymore. So this is going to slightly increase the mean water level at the upstream face of the dam. So this increase is the wave setup or wind setup. So this is the increase in mean water level, which in this case is the full reservoir level due to momentum flux. from the waves. So when you have waves acting or exerting some momentum transfer, then you would see the increase in the mean water level. So that is the wave setup. So you have to calculate both wave setup and the wind setup to get what is the free wall. So earlier we have calculated what is H, which is simply the full reservoir level minus formation level, and you get it to be 1 meters. Now, to get the wave height because of the locally generated wind waves, you can use these two empirical equations, like which is based on the wind velocity V and F. F is the fetch. So if you imagine you have a large water body, let's say this is from the top, you are seeing from the top you have a lake. So this is a lake and you are seeing it from the top, and the wind is blowing on top of the lake. So the wind is going to start exerting shear, and the waves are going to slowly start generated after a certain distance. So the shear is going to be exerted for, let us say, 1 kilometer or 2 kilometers on the surface, and then you would see slowly the waves start generated from here on. So it takes a certain distance for the wind to exert shear on the surface and generate the waves. So that is called fetch. So if your fetch distance is more than 32 kilometers, then the wave height is going to be a factor multiplied by square root of Vf, where V is the wind velocity and F is the fetch. Whereas if your fetch is less than 32 kilometers, then it's going to be the same 0.032 square root of Vf plus two more factors, plus 0.76 minus 0.27 f power 1 by 4. Now, these two are empirical. So these equations are derived based on a lot of data. So you can do curve fitting based on the data that you can collect from the field or from the laboratory experiments, and you derive these relationships. So the wind velocity V has units of kilometers per hour, and the fetch has units of kilometers. Now, in this particular case, the fetch is 20 kilometers and the wind speed is 150 kilometers per hour. So you can calculate the wave height to be 1.94 meters. So this is the wave height that is generated by the winds. So these are the wind generated waves. Now you also need to calculate what is the wave setup. So as I said earlier, wave setup is because of the increase in the mean water level because of the momentum flux into the water column. So you have wind waves that are approaching the upstream phase of the reservoir, and some of them might be breaking, creating turbulence. So that induces momentum transfer into the water column, and that is going to increase the mean water level. So this is the wave setup. And so again, the IS design code for dams has an empirical equation for the wave setup, which is a function of V square, which is again wind velocity, fetch, and D is the depth, the average depth of the reservoir. So here we are taking 15 kilometers as the average depth in the reservoir. So you would get an eta of 0.48 meters. So this is the wave setup. Or instead of using this equation, you can also use eta to be 0.2 times the wave height, or 20% of the wave height. So this is also again empirical, and this is based on data for beaches. So on the beaches, you have a lot of waves which are wind generated, and also because of cyclones. Now, a lot of measurements have been done by researchers across the world, and what they find is the wave setup is usually 20% of the wave height. So which when you calculate approximates to 0.4 meters. So to calculate the freeboard, we needed two quantities, which is the wave height HW, and then the wind setup or the wave setup. So the IS code states that for the wave height, you need to have a factor of 1.33. So to consider a design wave height, that is 1.33 times the wave height plus the wind setup. So your freeboard works out to be 3.1 meters. So the freeboard is this distance that you want to provide on top of the full reservoir level. So this FP works out to be 3.1 meters. So now the total height of the dam, which is H plus FP, would be 90 plus 3.1, which is simply 93.1 meters. So this would be your total height of the dam. So now you have the dimensions for the dam. You have the top width as 5 meters. The bottom width is 60 meters. And then the total height of the dam itself is 93.1 meters. So based on these dimensions, we are going to calculate the forces. So these are the dimensions that we came up with, and we are going to calculate forces on this dam and check if the dam is stable. So before going into calculating the forces on the dam, so this, if you look at the question again, you have some of the data given, which is the foundation level of the dam, which is at 110 meters above mean sea level, and then you have the reservoir full level or full reservoir level, which is at 200 meters, and you have the tailwater level conditions 115 meters, average wind speed, and then the fetch. So in reality, you may not have all of this data available readily, but you need to go into some records, or for example, to get what is the foundation level or bed levels at the site where you want to construct the dam, you need to do some survey to measure the actual bed levels. And then this full reservoir level you can calculate based on gradually varied flow calculations. So if you remember, let's say this is the channel slope, and you have the free surface, and the flow is from left to right. Now, let's say I put some obstruction here. Because of this obstruction, the water level is going to increase from here. So now you have downstream control. So based on this downstream control, you can calculate the water surface down upstream. So this is through GVF computations, which you might have done in hydraulics. So we are not going to go in details for this course about GVF computations, but in general, if you want to design any dam, you would also consider GVF computations. So only after you do that, you can estimate what is going to be the reservoir level. So before begin the forces and their moments on the dam, we are going to follow a notation where destabilizing forces are represented as negative and the stabilizing forces are represented as positive. So for example, if I sketch the dam, so you have hydrostatic pressure on the upstream. So it is a destabilizing force because it is trying to push the dam horizontally. Whereas on the upstream, you also have a small tailwater level, and it is going to exert force in the opposite direction. So this force is actually resisting the force from upstream. So this is going to be positive force, and this is going to be negative. So similarly, you can have the moments because of these two forces. So if it is clockwise, then the dam is overturning. So I would say that is negative moment. And if because of this force, the moment is on anti-clockwise, then that is positive because that is trying to stabilize the dam. So if you have uplift pressure that is trying to push the dam upwards or destabilize the dam, so again that is negative. Whereas the self weight of the dam itself, which is trying to keep the dam in place, so I would say that is positive. So this is the notation that we are going to follow for the calculating the forces. So starting with the hydrostatic pressure. So we have hydrostatic pressure on the upstream phase, which is 0 at the surface, and then it is increasing linearly. So this hydrostatic pressure is simply the area of this triangle. So in the previous lecture, we have seen the hydrostatic pressure is area of this triangle multiplied by the surface area of the dam. In this case, all the forces we are going to consider per unit length of the dam. So into the paper, we are going to consider 1 meter. So everything is going to be per unit length of the dam. So the hydrostatic pressure is half gamma h multiplied by h, and then 1 is the unit width into the channel or unit length into the channel. So your hydrostatic pressure on the upstream turns out to be, as I said, I have it as negative because it is a destabilizing force. It turns out to be closely 14 meganewtons. So kilonewtons is 10 power 3 newtons, and then you have meganewtons, which is 10 power 6. And this is going to act at a height of h by 3 from the base or from the bottom. Now we are going to consider the moments at the toe. So you have the heel part of the dam and then toe part of the dam. So we are going to consider the moments about the toe point on the dam. So which is on this figure, it is going to be here. So related to the toe point, the force is acting at a height of h by 3 from the base. And you can calculate the resulting moment because of this force. And I again represent as a negative because it is a destabilizing moment. So you have again hydrostatic pressure on the downstream. So the hydrostatic pressure again is similarly, you can calculate from the upstream, so which is half times gamma h bar multiplied by h bar multiplied by 1, which is the unit length or unit width into the paper or into the third dimension. And you calculate the force to be 122.7 kilonewtons. So make sure you represent the units. And I show this as positive because it is actually resisting the moments because of the upstream force. And it is acting at a height of h bar by 3 from the base, and you can calculate the resulting moment from this force. And next, we are going to calculate the uplift pressure. So here we are assuming a gallery is operative and it is at a distance of 10 meters from the upstream phase. So this is the gallery or drainage gallery, and we are saying that this drainage gallery is operative and it is acting 10 meters from the upstream phase. So in this case, you have a gallery here which is draining the water, and so it is at 10 meters from the upstream phase. So this is how the uplift pressure is going to act like. So you have a hydrostatic head of gamma h on the upstream side. On the downstream, you have gamma h bar. So if there was no gallery, then you would have the uplift pressure decreasing linearly from upstream to downstream. Whereas because of this gallery that you provided, you are releasing some uplift pressure. So the uplift pressure is going to reduce rapidly, and then from here it is going to again reduce linearly. So this is a magnitude that is given according to the IS code, where you have uplift pressure of gamma h bar plus an additional pressure because of the difference between the upstream and downstream phases. So you need to calculate the uplift pressure because of these different components. So what I'm going to do is simply divide all the upstream uplift pressure into rectangles and triangles. So you have U1, which is simply a rectangle here, and then U2 would be a triangle, and again U3 is a rectangle, and U4 would be a triangle. You can calculate the uplift pressure because of these individual components, U1, U2, U3, and U4. So the uplift pressure is the area of this region, and it is acting on the base of the dam. So we are considering per unit width or per unit length of the dam. So the area of this rectangle is gamma h bar, and then you have a total. So the total width is B, and this width becomes B minus 10. So your U1 would be gamma h bar multiplied by B minus 10 multiplied by 1, which is unit length. So you can calculate what is the magnitude of this. And then this is going to act at the centroid of this rectangle. So which is B minus 10 by 2. If your rectangle side is B minus 10, then it is going to act at B minus 10 by 2. Similarly, you can calculate U2, which is this triangle, and the resulting moment is going to act at 2 by 3. So 2 by 3 times B minus 10. So all the moments we are calculating with respect to the toe. So you are calculating the force and the moment with respect to toe of that force. So you have the resulting moment as negative again. So you can do the calculations. So U3 is a rectangle. So U3 is this rectangle, and the resulting force is going to act at the centroid of this rectangle, and U4 is this triangle, and the resultant is going to act at the centroid of this triangle. So that is what you will see here. U3 it would be the area of that rectangle, and then it is going to act at the centroid. U4 would be area of the triangle, and it is acting at the centroid of that triangle. Now all of this is with respect to the toe. So the uplift pressure and the hydrostatic pressure are very simple to calculate. So the hydrostatic pressure is simply the area of the triangle, and then the uplift pressure is simply the area of those each individual components. Now we are going to look at earthquake loads. Now when an earthquake happens, it is going to induce acceleration so it is going to induce acceleration on the soil and on the dam itself. So that acceleration could be either vertical or acceleration could be horizontal. So we are going to look at what is going to be the impact of this horizontal or vertical accelerations on the dam. And before we look at what is the impact of these horizontal and vertical motions, let us try to calculate the self weight of the dam itself. So the self weight is simply, if you calculate the area and multiply with the density, then you would get the weight of the dam. So here either you can just have two components, which is all of this as one rectangle and you have one triangle, or in this case I have just divided it into three components, W1, W2, W3. Now in some cases you may want to provide an additional component here for the dam, so that you increase the weight of the dam and also the resisting moments. So in that case, you need to calculate the weight of this component as well, W4. And you need to calculate the weight on top of this component because of water. Where in this case, in this example, we do not have W4. So we are not considering any vertical force of the water on the upstream phase. So if you just simply calculate the area and multiply it with the density or unit weight, you get the total weight of the dam. So W1 is a rectangular region which has an area of top width multiplied by C, and then you can calculate what is the resulting moment with respect to this point, because it's a simple geometry, or it's either rectangle or a triangle. So W2 is also a rectangle. So you have the area multiplied by gamma, which is the unit weight. You would get the self weight of the dam, and then the resulting moment because of this weight. And then W3 is a triangle, and this triangle is also going to resist the moments that are acting on the dam. So you can calculate what is W3 and then the distance from the centroid to the toe. So you can get the magnitudes. So every time you need to make sure you're using the right units. So either kilonewtons, newtons, or meganewtons. So once we calculate the self weight, we can calculate the earthquake loads on the dam itself. Now, if you have an earthquake happening, and if the motion of the dam is towards the upstream, let's say your dam, because of the horizontal motion of the acceleration of the earthquake, if your dam is moving into the upstream, then you're trying to push a mass into a still water body, and this still water body has to move because of this motion. So there is going to be an inertial force induced because of this sudden motion or sudden acceleration. So because of the horizontal acceleration of the earthquake, you are going to see an inertial force acting on the dam. So when you have the acceleration in the downward motion or upward motion, this is going to result in change of the unit weight. So unit weight is gamma times G. Now, if you have upward acceleration or downward acceleration, it is going to change this acceleration component. So your gamma nu would become g plus or minus a. So where a is the acceleration because of earthquake. So if you are moving down, if your earthquake acceleration is downwards, then your gamma nu is going to be rho g minus a. If your earthquake acceleration or motion is upwards, then your gamma nu is going to be rho g plus a. So now you have a new density of the material or new unit weight of the material based on which you need to calculate the forces. So now we are going to consider the horizontal inertial force itself. In this example, we are not going to consider the impact of the vertical acceleration. But if required, this is what you need to do. So you need to change the unit weight and recalculate the forces. So the horizontal force or the horizontal inertial force is mass times acceleration, where the acceleration is now alpha h multiplied by g. So usually when an earthquake happens, the acceleration because of the earthquake itself is a function of gravity, acceleration due to gravity, and multiplied by a factor. So in this case, alpha h. So your P or the horizontal inertial force is mass times alpha h times acceleration due to gravity. And mass times G is the weight of the dam multiplied by alpha h. So the horizontal inertial force because of the earthquake is the weight of the dam multiplied by a factor, which is alpha h, and this alpha h is a coefficient that we can generally assume take it as 0.1. Now this coefficient is going to change based on region. So if you have earthquake of certain magnitude, then alpha h is going to be a different value. And if your earthquake is of a different magnitude, then alpha h is going to be different. So maybe this we can look into details later if we have time. But for now, let us take alpha h as 0.1. So then, if you remember earlier, I had three components for calculating the self weight of the dam. Now for each of these components, I need to multiply 0.1, which is alpha h. So the horizontal inertial force on the first component is alpha h w1, the second component is alpha h w2, and the third component is alpha h w3. And they are going to act at these heights from the dam, from the base of the dam. Now that is because of, so this horizontal inertial force is because of the sudden acceleration of the dam itself. So you're trying to move an object that has been static, and now you want to suddenly move it with certain acceleration. So you have mass times acceleration. But you also have force or dynamic force because you're trying to move the water body as well. So you're trying to move two things. One is the dam itself, and then you're trying to move the water body as well. So because of this motion or acceleration in the water body, then you would have hydrodynamic pressure. So this hydrodynamic pressure varies with depth in the dam, as I showed you in the beginning. So this is how the hydrodynamic pressure is going to change non-linearly, and this pressure can be calculated using this equation where you have Cm is the pressure coefficient because of the earthquake. Again, alpha h is acceleration factor, and rho gh is simply your gamma h, which is the hydrostatic pressure. So you have the dynamic pressure is a function of hydrostatic pressure, but multiplied by some empirical coefficients. Now this Cm is again a function of another coefficient called C1, which varies with depth along the dam. So since C1 is changing from surface to the bottom of the dam or the bottom of the water column, you have changing hydrodynamic pressure. So that change is because of C1. And for vertical phase, in this case, because we do not have, so our upstream phase is vertical, we do not have any extension or any triangular portion. So Cm would be 0.05. But if it is not vertical, then your Cm value is going to be dependent on the angle of this upstream phase. So if your angle is changing, then Cm is also going to change. So in the exam, if you have to pick a Cm coefficient, the corresponding graph would be given, which is you have Cm here. You would have C angle theta of the vertical phase and then Cm, and there will be a curve. So based on this angle, you can pick what is the Cm going to be, and you can use that Cm value. Now this pressure, dynamic pressure, is varying with depth, and the resulting hydrodynamic pressure, hydrodynamic force is going to be this, so which is simply Pe multiplied by H with some factor 0.726. And then this is the moment because of this hydrodynamic pressure, which is H by 2, which is acting at a height. So you can calculate the hydrodynamic force and the hydrodynamic moments because of the earthquake. So you have two components because of earthquake. One is the initial force on the dam itself and the inertial force because of the water body, both of which you need to calculate. And then you have silt pressure, which is the additional load when you have silt on the upstream phase. Let's say you have some soil that has deposited in the reservoir, then you have some pressure because of this. So usually what you need to do is to consider the additional pressure because of the silt. So you assume the silt is going to act a pressure similar to hydrostatic pressure or hydrostatic force, but with a density of 360 kg per meter cube. So it's straightforward. You can calculate similar to the hydrostatic force, and the resulting moment would be at the center of the triangle. And then you have another minor forces where in regions where you can expect a formation of ice on the top of the water surface, then you assume the ice is going to exert a pressure of 250 kilopascals on the contact area of the dam. And for wind, usually you take the wind pressure is going to be 1 to 1.5 kilopascals. So the final thing to consider is because of the winds, again, as I said, there are going to be waves that are generated on the dam. So let's say this is your upstream phase of the dam and that's moving downstream. So this is how usually the velocity is going to be under waves, where you have maximum velocity under the crest, and then the velocity is going to reduce as you go down. And this is how the pressure is going to change. So the pressure is going to increase, and then it is going to decrease non-linearly. So for calculating this pressure and the resulting force because of this wind waves, the code gives these empirical equations, which is Pw, the pressure due to waves is 24 times Hw, and the resulting force because of the waves is 20 times Hw square. And it is going to act at a height of 3 by 8 Hw from the still water level or full reservoir level. So these are the different forces that are acting on the dam, but we have not seen or done any calculations on the stability of the dam yet, which we will be doing in the next lecture. So in the next lecture, we are going to see if the dam if the forces that we have just calculated are trying to destabilize the dam, or if the self weight of the dam is sufficient to withstand the forces acting on the dam. So that we are going to do in the next lecture. But so that's for today. So before I close the session, let's take any questions so far. Yeah, do you have any questions so far? Are there any questions?
Sir, please upload the notes.
Yes, I will do that. Yeah, and yeah, because this is my first time doing full lectures, you can also provide some feedback on how I'm doing. Feel free to send me an email if you want to see any improvements in the lectures. So I'll upload the notes on both Teams and on the Google Classroom, so you can download them. And I'll also upload the lecture recording that you can go through. So next class is going to be, I think, next week, if I'm not wrong. So if there are no questions, then we'll meet in the next class. Is that all right?
Thank you, sir.
Yeah, no problem. So feel free to get in touch if you need anything from me. All right. Thank you. Bye.
Thank you, sir.